two possible states, so 0 off, 1 on. So that's sort of the basic unit of computing is a bit. And as I sort of mentioned, that's why binary is very convenient when dealing with computers, because it gives us a very easy way to get a numeric representation or map from the data as it is stored on, say, the hard drive of your computer to a simple numeric representation that we can then make sense of and manipulate. So another key term that you will come across with respect to how computers store and deal with data is a byte. So a byte is a group of characters, a group of bit that go to form one, I suppose, machine character or one character. So nowadays, when people say a byte, they typically mean 8 bits. Historically, this is not necessarily the case. You will see some old architectures and old machines where you have, say, a 6-bit byte. You will see you will see various systems where you have non-8-bit bytes. But as a general rule, if you hear byte, think 8 bits. So you have a bit, which is a single atomic unit of information, and a byte, which is a collection of 8 bits. So each byte, 8 bits, so 2 to the power of, so 0 through to 2 to the power of 7, so that's 128 down to 0. So there are 256 possible different combinations, so 2 to the power 8 combinations that you can store, so everything from 0 to 255. But now your computer essentially just has your hard drive is just a large string of ones and zeros, so on and off, set or unset. But we're going to interpret it just as a really, really long string of ones and zeros. So I suppose then you could say, let's say you write down a section of your, or you visualize a section of memory just as a string of ones and zeros on a page. You might then want to ask a question, well, what does this data mean? And that's actually a somewhat complicated question to ask and answer, because the correct answer is it depends. You don't necessarily know. That string of ones and zeros, depending on how you wish to interpret it, could be interpreted as a text file. It could be interpreted as a Word document, as a PowerPoint document. It could be interpreted as an executable. It all depends on the method with which we wish to interpret that data. So this is where things such as encodings come in. So, for example, if we wanted to represent text, we then have to decide on an encoding that we're going to use to be able to interpret those ones and zeros as textual data. And there are a number of different encodings that you can use. ASCII is a famous and fairly well-known one. ASCII is the American Standard Code for Information Interchange. It essentially maps a set of 8 bits, so a byte, to an individual character. It actually only uses 7 bits out of that byte. So in effect, you get the ability to map 128 characters. Unicode is another text encoding that you can use. Obviously, so for English, you're probably okay with ASCII. Your 127 characters, you get your alphabetic characters, uppercase, lowercase. You get some punctuation. You get your various symbols, numeric characters. But you're going to run into problems if you want to start using other languages. So, for example, the Chinese alphabet, or if you want to start taking into account a number of European languages where you've got things like accented characters and some additional characters in the case of some languages. So ASCII, with its fairly small number of representable characters, isn't really sufficient. So there have been other encodings, such as Unicode is a very well-known one developed, that allow you to represent much, much larger sets of characters at the expense of taking a little bit more space for some. Unicode is actually a very clever representation in that if you want to take, say, ASCII, which is where it uses 1 byte for every character, ASCII is valid Unicode. So if you have a file in ASCII and a file in Unicode, they're not going to take up any more space. But if you then want to start going and adding additional characters to your file, so for instance, letters from, say, the Chinese alphabet, so you'll have to use more space for those, but it will only use more more data or more bytes for those characters that do not belong in the original ASCII subset. So that's actually really clever. But anyway, we'll go into a little bit of detail on that, just so you get a sense of roughly what's happening. But an in-depth coverage of Unicode and text encodings is not really in the scope of this course. I'm sure your tutor would be happy to go through it with you, and I'm also happy to cover it after the lecture or via email. So this is an example of the ASCII translation table for ASCII. So essentially a mapping from, you can see we've got a decimal number on the left, so we've got everything from 0 to 127. So everything that you can represent with those first 7 bits. Recall that ASCII only makes use of 7 bits. It uses 8 bits, so 1 byte for every character, but only really takes into account 7 bits. So there's 127 different characters, or 128 characters, sorry, 0. So you have your letters, uppercase, lowercase, some punctuation, some special characters to represent things like new lines, spaces, tabs. So yeah, essentially, what if you want to interpret a file of zeros and ones as an ASCII file, so it's a text file, you essentially look at each set of bytes, and you just use this ASCII encoding to map from each byte. So you work out what number that byte represents in binary, and then just map to the corresponding letter. So in that way, we can use the ASCII encoding to translate from just a file that is just a big set of ones and zeros to actual meaningful data. So that's something you can have a look at in your own time. ASCII is, as I said, it's only a subset of the characters that you may want to use, but it's okay for many things, particularly if you're just working in English and you only need the base English characters. So Unicode, as I mentioned before, so latest version of Unicode is well over 100,000 characters. So it's obviously has a much higher expressive power than ASCII. And as I mentioned before, UTF-8, so one of the most common types of the Unicode encoding, ASCII is valid Unicode. So Unicode is not ASCII, but ASCII is Unicode. And as I mentioned, it's really clever the way they do that. Essentially, they look at the first couple of characters in the string. If it starts appropriately, they work out how many bytes will be taken, will be used up to create the character that it's currently reading. And given that ASCII always starts with given that ASCII only uses 127 or uses 7 of the bits, they encode in the first. If it starts with a 0, you just treat it as an ASCII character. So that's so ASCII is valid Unicode, but Unicode is not necessarily ASCII. But yeah, so it's a superset of ASCII, covering a large number of scripts and characters. So you can see here, this is, I think, for the UTF-16. If you consider each block a set of characters that can be represented in UTF-16, you can see that only a very small section of it is set aside for Latin scripts and symbols, so that's sufficient. We've got things like, say, South Asian scripts take up a good chunk, a little bit for various European scripts. The bulk taken up by the various Chinese and East Asian scripts, so scripts where you have characters that map to specific words, so obviously much larger vocabularies of characters that you can have. And you can see that it's, you're able to represent with Unicode a much larger subset, or much larger set of possible characters. So as I mentioned, it's not essential that you understand exactly how Unicode works. If you'd like to know a little bit more about it, your tutor or I will be happy to take you through it. Always keen to have interested students ask questions like that. But it's a little bit beyond the scope of this course, so I think that's better for tutorials